Hello everyone, my name's Ben. I'm an iOS engineer at PlanGrid, where I also lead our multi-platform efforts. And today I'm going to talk about Kotlin native, that world, and how we make it work with coroutines inside of the PlanGrid app. Now, the first thing you need to know about PlanGrid is that it is a construction app for use on construction sites. So if you're a construction worker, you use this to keep track of your blueprints, issues, basically any workflow that you would traditionally think is being on paper. If your site uses the PlanGrid app, you use that to keep track of all of those workflows. So here we have a screenshot of the PlanGrid app. We're looking at a blueprint from the LA Natural History Museum. And there's a couple things going on here that I want to explain. So first, we have annotations. These are little markups that you can draw on the sheet, share amongst your team. We also have some relational data within your project. So here we have links to other sheets that might be relevant for your project. And then finally, we just have general data about the sheet. So we have the title and some version information. Now, as PlanGrid engineers, one of the things we're very concerned about is making sure that the app works well offline. And that's because it turns out that construction sites have bad internet. So the typical use case for the PlanGrid app, the way you use it on a job site is usually, especially on larger job sites, you'll have a back office somewhere where there is internet, and so you'll go there, download your PlanGrid project and all of the construction data, go down onto your job site, do whatever work you need, and periodically go back where you can get internet and sync any updates that you might have. So our app is very focused around sync. And because of that, we built this sync system and we're using it across multiple platforms. Over time, the sync system routes in different ways on different platforms. So it becomes this sort of cross-platform maintenance burden. Right, so this is starting to sound familiar, right? We're all here about multi-platform. This also adds a fixed cost to build features. So anytime you want to add a new feature to the PlanGrid app, you have to first build models and then persistence for those models, and then you have to hook that all into the sync system on your platform, right? So this is why PlanGrid we're invested in Kotlin native via Kotlin multi-platform. And for us, the three platforms that we support are Android, iOS, and Windows. Now, coming from the consumer world, Windows, usually a little bit shocking. But in the construction world, construction teams do quite a lot of work on Windows machines. So we support a Windows app as well. And consequently have probably most of the Windows engineers that don't work at Microsoft. With our multi-platform project, what we're trying to do is sort of keep a shared understanding of sync in our multi-platform library. So that's what we're trying to build. That way we can build all of those fixed costs like models, persistence, and sync, keep that all in one place, maintain it in one place, and distribute it to all three of our platforms. So within the library, there are a few pieces of sync, and I'll talk about what we're using for them. So first, for serializing JSON, so you get a JSON sync response. We serialize that using Kotlin X serialization. All three platforms use and store data using SQLite, and for that we're using Square's SQLite. Thank you, Square. And so to understand this a bit better, I've made a graphic that sort of encapsulates all of the different pieces that we want to share in this library. So you can think of sync starting at the top with the sync coordination layer, and that's what's going to decide which data to sync and when. And maybe we don't need to sync at all because we're up to date, right? And then underneath that, we have the things that we actually want to sync. So sheets, annotations, and then a bunch of other model types that I'm not going to go over. But so that gives you sort of a sense of what sync is looking like. And then within each sync task for each syncable type, that's where we do our JSON and SQLite work that I just mentioned. Now, if you're coming to Kotlin and you're trying to figure out how you want to manage all of this, because sync is something that happens in the PlanGrid app in the background asynchronously while the user waits for sync to go. And the best way to manage asynchronous work, in my opinion, in Kotlin, is to use coroutines. So ideally, we can use Kotlin coroutines as part of our shared sync coordination layer to handle all of the asynchronous work. Now, to understand how we're going to do that in the multi-platform library, we need to take a look at the state of coroutines in the native world. And to talk about that, we need to discuss something called the coroutine dispatcher. So if you're familiar with the coroutines at all, you may have seen this before, but the coroutine dispatcher is the class that behind the scenes does all of the heavy lifting of when you write coroutine code, the coroutine dispatcher decides where that code actually gets run. So I have a little diagram here. So you start with some coroutine code. It's going to go execute. Behind the scenes, the Kotlin coroutine library will send that through to a coroutine dispatcher. And then based on the dispatcher you choose, that's going to decide how to run that code. Now, if you don't pick a dispatcher, it's going to use dispatchers.default. You may have seen this singleton before. And on the JVM, this goes to a background pool, a pool of background threads, essentially. So on the JVM, it'll look something like this. It'll have a pool of some threads, and it's going to pick one of them to essentially run your coroutine code. And so, again, on the JVM, all of this works as expected. Now, in the native world, so for me, that means iOS, and also for PlanGrid, it means Windows. Things are a little bit different. And so it's really important to understand how nice it is to have a working dispatcher in the JVM world. And what that means is, if we wanted to make a sync worker class, we could write something like this. So here we have this sync work class. It implements coroutine scope. And so we'll define our coroutine context, which is just a plain job. So since I didn't specify a dispatcher, it'll use the default dispatcher. And what this means is that if I want to start sync, I can write a start method like this. And then we can go ahead and call launch to launch our coroutine. It'll run off in the background and start doing our sync work. And the really cool part about this is that if I decide I need to stop sync early, I can just call coroutine context.cancel. And because of all the structured concurrency goodness that comes with Kotlin coroutines, it's going to cancel all of the child work associated with sync that's going on right now. So that's pretty exciting, especially for me, coming from iOS, where we have GCD and we have to kind of manually manage all of this ourselves. It's quite a pain. Now, again, this is what your code might look like if you're working in the JVM. But if you try and take the same code and run it in native, you'll get this error. It says, there's no event loop, use run blocking. And so what that means is that we essentially now have to figure out how to take sync, this sort of complicated, multifaceted thing, and relegate it to a block that looks like this. We're going to call do sync, and inside of run blocking, we're going to try and figure out how to do all of our sync. And if you've never seen run blocking before, or maybe you went through the Kotlin guide on their GitHub and sort of saw it and then tried to forget about it, well, there's 3 things that you should know about run blocking for this talk. So first, run blocking starts an event loop so that you can do asynchronous work with coroutines. If event loop is like a term you've seen before but not super familiar, you can just read this as fires up coroutines. Furthermore, run blocking is going to block the current thread. So that block of coroutine code that you're going to pass to run blocking is going to block the current thread until all of that asynchronous work is finished. And then finally, and this is especially important for native, all of the coroutine classes like coroutine scopes, context, everything that gets created while you're using run blocking, that has to stay confined to the current thread. So you really are stuck on that thread when you use run blocking. So today I'm going to talk about this library that we wrote at Autodesk/PlanGrid to sort of help work around this situation while we're waiting on multi-threaded coroutine support for native. And to do that, we're going to look at the two important functions from coroutine worker. The first one is called execute, which just takes a block of coroutine code and offloads it into a worker pool to run. So you don't have to think about threads at all, or at least not more than it's going to run in the background. And then we're going to talk about this other one called perform and wait. And this is something that on the JVM you might reach for instead of using like with dispatchers.io. So essentially you're in a coroutine context and you want to perform some work while you suspend the current coroutine waiting for it. And I have another diagram for that later, so don't worry about remembering that right now. So again, today we're going to build these 2 pieces of Autodesk coroutine worker. So you can kind of see what you actually are and are not boxed into when it comes to Kotlin native and coroutines. And to start, I first need to go over the mutability and concurrency rules of Kotlin native, because that's very important to understand to really get into implementing any of this. And once we have a good handle on that, we're going to go into implementing execute, so essentially creating our coroutine worker pool. And then finally, for sort of the grand finale, I guess, we're going to implement perform and wait, which is a bit trickier. Now, again, I'm an iOS engineer. If you dialed in maybe just a little bit after I said that. So when I first got started in mobile development, I was in Objective-C, where we called lambdas blocks. And then Swift came along, and we called them closures. And now I'm working with Kotlin, where they're called lambdas. So I've made this handy guide for you here, in case you're not sure like what I'm saying when I say closure or block. So if I slip up, which I undoubtedly will, I might even just say block the whole time. Who knows? That's there for you. So feel free to write that down or not. All right, so jumping right in to mutability and concurrency in Kotlin Native. The first thing that you need to know, and hopefully at least the one thing that you should remember coming out of this, is that when you create an object in Kotlin Native, that object is considered owned by that thread, which means that accesses to that object from other threads are essentially strictly not allowed. And those will be enforced those rules are enforced by the Kotlin Native runtime. Now, there are two ways to work with objects across threads in Kotlin Native. The first is you can transfer that object. So essentially say, okay, this object was owned by thread 1, now it's going to be owned by thread 2. So I have a little graphic to illustrate that. So here we have two threads. And let's say we create an object on thread 1. Now, once we can verify that there are no more references to that object on thread 1, it's now safe to transfer that to thread 2. And I'll get into that some more in a minute. Your other option is you can freeze the object. So here I'm going to create an object again. It doesn't matter what thread I created on. We can call someObject.freeze, and that object becomes immutable. So by immutable, that's something the Kotlin Native runtime will enforce for you. So after you freeze an object, we just say that it's frozen. And if you try to mutate some variable on that object, Kotlin Native will throw an exception saying, hey, you tried to mutate something on an object that's been frozen. All right. The other API that's important to understand when doing any kind of threading work in Kotlin Native is the worker API. It's a class, and you can just read this as worker thread. Essentially, a background thread is not the main thread. And it has one important function that we care about today, which is called execute. And I like to say that execute takes an object, transfers it through a producer for use in the background. And I'll show you what that means, and we'll work through an example, because that's a bit of a mouthful. So let's say we have a pair of numbers. We'll call them add these, because we're going to add them. And then we have access to a worker instance, and we're going to call execute to add those two numbers in the background. And the first parameter you have to pass is the transfer mode. You can pass safe or unsafe. I'm pretty sure most documentation recommends passing safe. I haven't tried unsafe yet. If you do and have good results, let me know. But essentially what this means is that Kotlin Native is going to safely transfer that object to the background following all those rules I just laid out. The next comes that producer block that I mentioned. The whole job of this producer block is to essentially return an object to then transfer that object through for use in your background Lambda. And then finally, you pass it the Lambda that you want to execute as your background work. And so again, add these becomes the parameter for that block. And here I've just added a line where we're going to print the result of adding these two numbers together, right? Now, if you try and actually run this code, it seems like everything might be fine and good. You'll actually get an exception that says illegal transfer state. And this is where people coming to Kotlin Native might throw up their hands, because one is very vague. I don't think there's any line numbers with it. But hopefully you will have just written this, so you'll kind of know where it is. Again, there are two things we can do to fix this, but first I'll talk about why this happens. So it turns out that when we created a reference to our pair, that actually incremented the reference count by 1 on that thread. And so then when Kotlin Native went to go transfer or add these to the background, it says, hey, there's still a reference on this thread, it's not safe to transfer it, illegal transfer state. Okay, well, I just told you how we're going to, those two rules, there's two options we have for figuring out how to deal with the situation, so we'll look at option 1. So the first option is just to essentially create the pair inside of our producer block. Now personally, I find this solution to be pretty uninspiring, especially if you're coming to Kotlin Native for the first time. You have to think, okay, well, how in the world am I going to scale creating objects inside of producer blocks to do all of my background work that I need to do? And most background work use cases are a bit more complex than just this, right? So that leaves us with our other option, which is a bit simpler, which is we can just freeze the pair when we create it. So we'll call .freeze. Pair is now immutable, and we can safely transfer it for use for doing our background work, no problem. And in this case, it's fine. Pair is immutable anyway. We're just going to be adding the two numbers and then maybe doing something with the result later, and in this case, printing it. And this is the simplest approach in my mind. And because it's so simple in terms of, I can wrap my head around when I freeze an object, it becomes immutable, and it's immutable from then on out. That's the approach that I've taken and that we've taken with Coroutine Worker, is that we decided essentially we can wrap our head around this and we can adopt our mental model to program in this way, to program with frozen immutable state. And outside of Kotlin Native, there's a whole discussion about working with mutable versus immutable state, right? So there may be other benefits you can get to working this way in general. Thinking about our mental model, this works well in particular for background work that just needs to produce a result. So you take some input and then produce a different output. This also works particularly well for sync, which is how I got here in the first place. And so if we think about sync as sort of a series of immutable transformations, we start with our network data. From there, we use Kotlin serialization, transform it into wire types. From there, again, transform that into database types. And then from there, store it in SQLite using SQLite, right? So we can sort of work with frozen data all along this to do the sync work that we need to do. Shoot. So this half of the graph is actually not specific to sync at all. You can use this pattern for doing network calls and translating that into native types in the background outside of the PlanGrid sync use case and sort of reuse that for that as well. So just something to note if you're thinking, well, this is only going to work for sync. So some other things to note about freeze. It's not exactly a silver bullet. There are definitely ways you can get into weird situations with that as well. So it's actually not super hard to freeze large object graphs by mistake. And that's because of something I haven't told you yet, which is when you freeze an object, not only do you freeze that object, you freeze everything that that object references recursively. So something to be aware of. And knowing that, there are tools to help you get out of these bad situations. So arguably the most important one is this API called ensure never frozen. When you call this on an object, then anytime after that, Kotlin Native runtime will throw an exception if you attempt to freeze that object. So I want to show kind of an interesting example that I've run into with this before. So to look at this, we're going to take the example from before and just lift it up into a class. So here, add these is now an instance variable. And then we're going to create a function called doWork. It's going to take that work block I made before, wrap it into a Lambda, and freeze it. And Lambda is an object like anything else, totally fine to freeze. However, you have to be aware that, like I said before, if you freeze an object, you're going to freeze everything it references recursively. And in this case, because add these is an instance variable, right here we are implicitly capturing this inside of our Lambda, which means we, maybe by mistake, are going to freeze the entire sample instance and everything it references as well. So again, you can save yourself here by just using ensure never frozen, add an initializer that calls this.ensure never frozen, and instead of throwing an exception sometime later on down the road when you try to mutate your object and then find out by surprise that it's frozen, you can add this here and it'll throw an exception right at the moment that you go to freeze it. And if you want to actually just get yourself out of this situation entirely, there's a way to fix it. So we can just grab a local reference to our instance variable, and it'll only capture the instance. It'll only capture our local variable instead of capturing this. All right. So that's sort of a whirlwind tour of mutability and concurrency rules in Kotlin Native. And now we have what we need to be able to implement our coroutine worker pool. So we're going to go and get into implementing execute. But before we get into that, I talked about the coroutine dispatcher, and if you're familiar with the coroutines library, you might know that the coroutine dispatcher is a public abstract class. So you might be thinking, well, maybe we can just take that abstract class and fit it into the native box, figure out how to make it work in the Kotlin native world now that we understand all the rules, right? Okay, so let's just look at doing that real quick. So it has one important method that we care about implementing if we're going to do this, and it's called dispatch. This is the method that coroutine dispatcher calls when it wants to take a block of coroutine code and execute it somewhere. So our job is to figure out, what do we do with this block? Because we have to abide by Kotlin Native's concurrency rules. So we have two options again. The first is we could try and take that block and transfer it to a background thread. The only problem there is that I already know that the block is held onto by coroutine internals, so you won't be able to transfer that. You'll get the illegal state exception again. You could try to freeze it, but first of all, you don't really know what that block is. It's just a runnable, which is backed by some concrete implementation. But it's fine. I already know for you, again, that it's backed by some internal coroutines class, which does have mutable states. So later on, you'll cause some other invalid mutability exception if you go try to do this, essentially. But philosophically, unless you name this dispatcher appropriately, you don't really know if it's what that block of code is and whether or not it's really safe to freeze it. So the sad answer is that we essentially have to wait for the magic that fixes issue 416, which is what I'm going to call it from here on out. Issue 416 is the Kotlin Kotlin coroutines issue asking, please fix this in Kotlin native, multi-threaded coroutines. All right, so we're back to trying to figure out what can we do with just run blocking. And so right now, the state of things is that we can't switch between threads inside of coroutine code when we're using run blocking. So if you're going to try to reach for with context or something to switch to another dispatcher to do work somewhere else, that's not going to work in Kotlin native. But what we can do is we can pick a thread before running the coroutine code, and that's basically just a worker pool. So we're going to go ahead and implement a worker pool. So the first step is we're going to take our worker and essentially make it so that we can run blocking, run coroutines in the background. So to do that, we're just going to go ahead and drop run blocking into place. And now we have a place where we can run coroutines in the background in a worker. The next step is what we want to do is essentially abstract all of the details of worker so that we don't have to think of them. We want to be able to take a block, an arbitrary block of coroutine code, and run it in the background. So to do that, we're going to create this perform work method. The work block here has the same signature as the run blocking block. And so now what we can do is we can take that work block, freeze it, because again, coroutine worker takes the approach of let's just try and work with frozen mutable states. So we're going to freeze that work block and then transfer it across so that we can run it inside of run blocking in our background thread. Right? Freezing the work enclosure. And that's it. So now we have this API that extracts the details of a worker specifically. And the final step to doing this is we essentially have to throw in more workers. So we're going to go ahead and write the worker pool class. First step, create an instance variable that contains all of our workers. In this case, I picked 5. So we're going to go with 5 workers for our pool. You could make this number variable in an initializer or something. And then we're going to create this worker index variable. And this is going to use a class I haven't showed you yet called atomic_int. You may have seen similar atomic primitives on the JVM. In Kotlin native, it's a little bit special though, because atomic_int you can freeze, and even though it's frozen, you can still mutate it from other threads. And that is sort of the secret to using Kotlin native in the multi-threaded world, is finding these classes that sort of have exceptions to the rule and figuring out how to use them to do what you want to do. So here we're going to use atomic_int for our worker index so that we can pick a different worker each time to sort of round robin in our pool. And then we're going to go ahead and freeze our worker pool so that it's safe to use for multiple threads without any issue. And then in our perform work function, all we have to do is add a little bit of code to pick a worker. So each time we call perform work, we'll increment the index, mod it by the number of workers that we have, and that will give us kind of a round robin choosing workers. And then finally, we're just back to what we had before with taking our work block, freezing it, and passing it to run inside of run blocking. So now we have a worker pool that we can use to run coroutine code on multiple threads in native. And this doesn't publicly expose anything about the worker API, which is only available on native. So you have something that you can define an expect class for and implement something similar on the JVM, which is almost exactly what coroutine worker does. All right. So we've covered mutability and concurrency. We now things got real with our coroutine worker pool. We're already using all the pieces of worker. And so now I want to talk about perform and wait. which is all about doing work across threads, and I'll show you more about that in a moment. Before we get into it, though, we need more tools to get there. So the first tool I want to talk about is called atomic reference. Similar to atomic int, only it can hold arbitrary references to objects, but specifically it holds a reference to a frozen object, and that's important too. And atomic reference is similarly special. When I say special, it's really just because it's backed by C++. It's actually not that special. But atomic reference, you can freeze it and mutate its value for multiple threads. So you can, for multiple threads, change what that atomic reference is referencing, right? And again, the magic is that you can update it for multiple threads, and this is going to be sort of the trick we're going to use to get what we need done. So here I have just a quick sort of snapshot of the API we're going to use. There's a bit more to the atomic reference interface, but this is the important part. We can initialize it with a starting value, and then it has a variable that we can use to mutate it later on. Next is a pretty interesting one, stable ref. I didn't expect that I was going to use this for doing multi-threaded work. I believe stable ref is actually created for passing Kotlin objects through C callbacks and stuff, but it has a use case in the multi-threaded world, which I'll talk about. So a stable reference essentially stably references an object, which outside of the C world actually sounds kind of weird now that I say it more out loud. But okay, so it has some interesting tricks, and I'll just walk you through some code to show you. So this is how we create a stable reference to an object. We could do stable ref.create, and then we can also freeze that reference. And the interesting thing about when you freeze a stable ref is that it doesn't freeze the thing that it's referencing. Again, breaking the rules that I told you earlier, where I said when you freeze something, it freezes everything and references recursively. Stable ref, that's not true. So we can use that to essentially reference an object that needs to stay mutable and hide it as we pass it along through threads, so that later on we can bring it back to the thread that owns it and do stuff with it. So again, we're going to do that, and here's the APIs for doing that. So later on, you can call ref.get to unpack it, and you always want to make sure to dispose of your stable refs, because when you create one, it increments the reference count. Dispose will decrement it again. So don't leak memory, use dispose. All right, other tool that we're going to need to get there, atomic int. Already kind of touched on this before. I guess it's worth mentioning that there is also atomic long if you need a wider integer for whatever it is you're doing. And here's the API for atomic int. It's the same for atomic long, just int long. Main difference from atomic reference is that it also has an API for atomically doing addition or subtraction with the integer that it's wrapping. All right, so we have the tools. That's all we need to do what we need to do with perform and wait. Now again, I've been talking about perform and wait a little bit, and I've been talking about it pretty fast, but I have a very nice graphic for you. It's not going to win any awards or anything. It's not that nice. But so let's say we're on thread A, and we're parsing some JSON, all right? And then we do something else. And now we decide, OK, we need to do some SQLite write work, and we don't want to block the current thread doing that. So this, on the JVM, this is where you would reach for with context dispatchers.io, and that's going to suspend the current thread while it goes and does I/O work using the I/O dispatcher. Well, we can't do that in native yet, so that's where perform and wait comes in. Perform and wait, we are going to pass it the work that we want to happen on another thread, and that's going to go out to the worker pool and push the write to SQLite over there, and let's say it picks thread B. And while that work is happening, perform and wait will suspend and wait for the result of the write to SQLite. And so it's going to suspend, so it'll be non-blocking. It'll free up the current thread to process any other coroutine work that might be scheduled on that event loop. And so this is sort of the big magic trick here, is figuring out how do we, non-blocking, wait on one thread, wait for the results from some other work on another thread, and do this all in the native world. Because again, it feels very constrictive looking at it from just, I have to use run blocking, I have to stay on one thread. So let's start. We're going to just jump right in and start implementing perform and wait a little bit at a time. So with perform and wait, the first thing we need to do is suspend the coroutine. So we're going to call this API from the Kotlin coroutines library to manually suspend. That'll give us access to the continuation so that when we know that the work on the other thread is done, we can manually resume it ourselves. And then we're going to make our perform work call. You've seen perform work. We just implemented it. And then we're going to do the work that we set out to do. Now here I put it inside of run catching. I believe it's either from the standard library or from Kotlin Coroutines. But essentially, what it does is it wraps that block, and it'll capture any exceptions and wrap that into a result. So that val result will actually be a result type. Now the question is, what do we do with that result? How do we, we're on some other thread somewhere else in the pool. How do we get that back so that we can unsuspend and resume with the result of that work we did? So to do that, we have a couple of options. If you've done any native work, you may have seen that there is an API for a future. So we could try to use a regular future, but when you access the future's result, that'll actually hang the current thread, sort of defeating the whole point of this, right? We want to do this in a non-blocking way. If we wanted to block the current thread, we could just do this SQLite work on the thread that we were already on. So we're not going to use a future. Coroutines also has a mutex, which when you use lock and unlock, lock will, is it lock? I think one of them suspends. Anyway, it's a suspendy mutex. The problem is, again, issue 416, mutex is not ready for use in Kotlin native for use on multiple threads. All of its ownership rules apply. So that leaves us with kind of a not so great option, but it does work to get what we need done. And that is to essentially delay and use an atomic reference and wait for our work to appear. So what we're going to do is essentially keep a local atomic reference, which again, safe to freeze and safe to update from another thread. And then in another coroutine, but on the thread where we started, we're going to just loop, wait for that result, and delay. And that delay will sort of repeatedly suspend, freeing up the current thread to process any other coroutine work that might be scheduled or might need to happen. So again, accomplishing our non-blocking. All right, so let's go ahead and implement this. So first step, we're going to add that atomic reference that I was talking about. This is going to eventually hold the result of the work that's going to happen on the other thread. And then we're going to launch our waiter coroutine. So this is going to launch and essentially spin and delay, wait for the sort of final result of that work to appear. And once we're outside of the loop, we know that our cross-thread work is done. And then we have one minor update to do to our suspend coroutine code, and that is once we know the work is done, we'll update the result ref across threads to signal that the work is done. All right? So this is sort of a suspendy feature that we've cobbled together for this use case. And yeah, again, just in case you didn't see it, updating the result on complete. All right, so now the question becomes, how do we resume? Once we have the result and it's there in our atomic reference, our while loop has bailed out, how do we actually get that continuation and resume it? Because we got access to it down here, but we need it back over there. So that is where StableRef comes in. That was that sort of weird tool I was telling you about before. So we're going to use StableRef to essentially hide the continuation, which needs to stay mutable. We can't freeze it because Kotlin Coroutines needs to do stuff with it, mutable stuff with it later. To essentially hide it, pass it along, and then put that in with our result ref, so that the result ref, then when it's set, has both the result and the continuation there together for us to resume it. So we're going to go ahead and do that. So step one, we're going to update our atomic reference to have a more scary looking type signature. So instead of just holding a result, it's going to hold a pair of things, the result and a stable reference to our continuation that we're going to need when all of this work is done. And then we need to do a little bit of an update to our suspend coroutine function. When we get access to the continuation, we're going to hide it inside of a stable ref. And then when we're done with the work, we'll set a pair of our result and a continuation so that we can resume it together in our result ref. Then, back in launch, we just have a little bit of unpacking to do when we're done. So now when we're done, the result ref is going to have both the result and the continuation. We unpack it, and then we can resume the continuation with our result. And that sort of ends the basics of how perform and wait works. And now we've done sort of the impossible, I guess, depending on your view of Kotlin Native when you first come into, which is doing coroutine work across threads within the Kotlin Native world. And we didn't have to think really very much about workers. We had a pool do that for us. So that is the basics of coroutine worker, execute, and perform and wait. Coroutine worker handles a little bit more. There's no time for that today. But some of the things it can do is, in coroutine worker, execute actually returns a handle to the work, and you can cancel it. I now kind of debate this that I wrote better scheduling, but it does a different way of doing scheduling within the worker pool, and you can take a look at that online. Coroutine worker is open source. It also encapsulates some sort of shared understandings about how atomic reference and things works within Kotlin Native. So atomic reference, if you don't clear it out, it will leak its memory, and coroutine worker is sort of aware of that and other idiosyncrasies about Kotlin Native, and sort of we keep all of that wrapped up in coroutine worker so we don't have to see it. So just to review what we did today, it was quite a bit. We went over the Kotlin Native concurrency model. If you're coming from the JVM, hopefully that was a decent introduction. We talked about some strategies for working inside of the Kotlin Native concurrency and mutability model when it comes to working with frozen state or state that can't be frozen. And for those, we use atomic reference. We need to work with frozen state. Stable ref if you need to sort of pass some stuff around but keep it mutable. And then we went through and understood the basics of coroutine worker. And in my opinion, this is sort of the best that we can do in terms of multi-threaded coroutine-like work inside of our code until issue 416 is fixed. And so there's active work going on with that in the Kotlin Native, in both Kotlin Native and in coroutines. So hopefully one day we can throw out coroutine worker, and this talk will be just like a thing that I put next to deprecated when that happens. So if you have any questions, here's the coroutine worker link. Here's my handles. If you have any questions, come up and talk to me. And thank you for listening.